Okay, chemistry. We're now on to a really important topic in acids and bases, and this is on the subject of buffers. So what is a buffer? A buffer is a conjugate acid-base pair designed to resist changes in pH if small amounts of acid or base are introduced to the solution. So human blood, for example, contains a buffer of carbonic acid and its conjugate base, the bicarbonate ion, in order to maintain the blood pH between 7.35 and 7.45. A blood pH value higher than 7.8 or lower than 6.8 can lead to death. So buffers are really important in biological systems, especially to keep living organisms alive so they don't become too acidic or too basic, too alkaline. So buffers are created from a conjugate weak acid that will neutralize hydroxide, OH- ions, and a conjugate weak base that will neutralize hydronium, H+ ions. Neutralized H+ and OH- become neutral H2O molecules. Buffers must be created from a conjugate weak acid-base pair. A random acid-base pair will react with each other in unpredictable ways and cannot act as a buffer. So acetic acid CH3COOH and the acetate ion CH3COO- can act as a buffer because they are conjugates. Acetic acid, though, and the fluoride ion cannot act as a buffer because they are not conjugates. So acetic acid and the acetate ion are a conjugate acid-base pair. The acetic acid buffer defenders will guard against the strong base invaders. So there we have strong base invaders. So these are the OH- invaders. They were produced when 3 NaOH molecules dissociated. The OH- invaders want to raise the pH of the solution. They want to move it up towards 14 on the pH scale. These are the acetic acid defenders of the solution. They want to protect the solution from pH change. So you have a strong base attacking the solution being defended by weak acid defenders. When a defender fights an invader, both will neutralize and no longer exist. As long as there are more defenders than invaders, the solution will be protected and the pH will almost not change. So what you have to remember is that when you have hydroxide ions in the solution, a weak acid will 100% of the time donate a proton to the hydroxide, not to a water molecule. So what it's then doing is it's neutralizing the hydroxide, the OH-, and turning it into a water molecule, which is neutral. That doesn't change the pH of the solution. So let's see how this works. Okay, so there's the weak acid defender has a cannonball. That cannonball is a proton that it's going to donate to the hydroxide. So it fires the cannonball at the invader, and what happens then is the invader turns into a water molecule. Now what happens to the weak acid defender? It's already fired its only cannonball, so it's going to become an acetate ion, and it's going to go down into the solution. All right? So what you've done is you've traded a hydroxide, OH-, a very strong base, for a weak base, which is the acetate ion. So there's a second cannonball. A second defender is going to fire its cannonball at one of the invaders. That's an OH-. You add the H+ to it and it becomes a water molecule. Then the defender, the acetic acid, has then lost its proton, so it then becomes an acetate ion, CH3COO-. Finally, we have one more invader. We're going to fire a cannonball at that one, turn it into a water molecule, and then that defender becomes an acetate ion and goes into the solution. So what you've done is you've dropped 3 bases, acetate ions, into the solution. Isn't that what you didn't want to happen? You don't want it to become more basic? Let's just take an example. If you had 10,000 OH- going into the solution, that would turn the solution totally basic. You'd have 10,000 OH because that's what makes a base, is the OH. If, on the other hand, you defended with 10,000 weak acid molecules that would then turn into acetate ions, then you'd have 10,000 acetate ions in the solution. Now let's say that only 1 out of every 10,000 acetate ions causes a water molecule to break apart, because that's what weak bases do. They break a water molecule apart, they pull a proton away from it, and turn the water molecule into a hydroxide. So that's a good trade-off. If 1 in 10,000 acetate ions breaks a water molecule apart and creates a hydroxide, that's only 1 hydroxide. If that weak acid had not been there, then those 10,000 hydroxide ions from the strong base would have been in the solution. So you traded 10,000 hydroxide ions for 1. That's a good trade-off. So even though the acetate ion that you see in the solution is a base and it's going to create some hydroxides, it's not going to create very many compared to how many would have been dropped in there by the strong base. So there are no invaders left, but there are 2 defenders. The pH remains almost unchanged. The acetate ions in the solution, as I just said, slightly raise the pH, but not nearly as much as the OH invaders would have. The solution also has acetate defenders to protect against strong acids, but they're not needed in this particular reaction. We'll see them in the next reaction. So now we're going to have strong acid invaders. So these are hydronium ions, H+ invaders from a strong acid, HCl. They want to lower the pH of the solution into the acid range. So they want to take it down towards 0 and 1. These are the acetate ion defenders. They're the weak base in the solution. They want to protect the solution from pH change, and they're going to do that when the HCl throws off and donates its proton. Instead of going to a water molecule and creating an H3O+, a hydronium ion, which is exactly what you don't want to happen, these defenders are going to catch that proton and defend the water, the H2O, from becoming H3O+. So let's see how that happens. So the CH3COO- buffer conjugate base defenders neutralize the H+ strong acid invaders by accepting a proton until one of the 2 of them runs out. So there's a cannonball. That's an acid. It's going to give off a proton and it's going to throw it, and one of the defenders is going to catch that proton so it doesn't hit a water molecule. That turns that acetate ion into an acetic acid again. It goes back to becoming CH3COOH. So it did not become an H3O+. And what happened to the HCl without its proton? It's now a chloride ion, Cl-. Now, even though Cl- has an electrical charge, it's an anion, from an acid-base standpoint, it's neither an acid nor a base. It's not going to accept a proton. It doesn't have any protons to give off. So it's neutral in terms of being an acid and base, so it doesn't affect the pH of the solution. Now we've got a second invader. And this one's going to throw off a cannonball, a proton, and that's going to hit one of the defenders. The defender's going to intercept it and then go into the solution as CH3COOH, and that HCl molecule will turn into another chloride ion. Now we have a third one. This one's going to fire a cannonball, turn the acetate ion into an acetic acid molecule, and then the HCl again turns into a chloride ion. The fourth one, same thing. There goes the acetic acid and a chloride ion. The chloride ions actually are in the solution, but for our metaphor of the 2 armies battling here, we're showing them on the outside. But all of this is happening inside the beaker, actually. Finally, we've got one more defender. So this one's going to fire a cannonball at that defender. It becomes an acetic acid, a weak acid, and that attacker becomes a chloride ion. When a defender fights an invader, both will neutralize and no longer exist. This time, there are more invaders than defenders. So the invaders win and change the pH of the solution. So when all the buffer defenders are gone, the remaining strong acid invaders are free to pass protons to H2O molecules and create hydronium ions. This will lower the pH down into the acid range. the buffer has been defeated. So there goes the acids in there, and they become H3O plus hydronium ions. That's what you didn't want to happen, but you didn't have enough of the defenders to defend against all of the invaders. pH will hold only as long as there are more buffer defenders than invader strong acid or strong base. Okay, now we're going to talk about salts. To create a buffer, you must understand what a salt is. When an HF, hydrofluoric acid, weak acid molecule dissociates, it produces its conjugate base, a fluoride ion, F-. So the HF and the F- differ by exactly one proton, and that's the definition of a conjugate. This is a reversible reaction, so the fluoride F- base can take back the same proton or a different one. So again, in a weak acid or weak base, they can accept and give off protons, and that makes them reversible. That makes it a reversible reaction. The fluoride ion F- is the conjugate base of HF. A salt is a neutralized acid or base. Neutralized means that it is not an acid or a base. So a salt is formed when a 1+ cation, such as sodium Na+, attaches to the conjugate base F-, or some other weak base. So what you just saw happen was a proton leaving the hydrofluoric acid. So now you have an F- over there as the conjugate base. So if the proton came back, it would be hydrofluoric acid again. But what if something else? A proton has a 1+ charge. What if something else with a 1+ charge that wasn't a proton decided to attach there? In this case, you see a sodium ion. You know that sodium is a 1+ charge by looking at your charge number by ion sheet. So what if it went over and attached to that fluoride? So it's going to do this. So the Na+ and the F- form an electrically neutral ionic bond, cation, anion. This bond will only form out of water but will dissolve 100% in water. So the fluoride ion F- and any cation such as Na+ form a basic salt, a neutralized base. So the base is the fluoride ion F- because it can accept a proton, and that's the definition of a base. But what if it accepts something else other than a proton, such as a sodium 1+ ion? Then it's neutralized. It's not an acid, it's not a base anymore, it's neither one. So that's called neutralization. And that's called a basic because it's formed from the base F-, salt because it's neutralized. That's what salt means. It means a neutralized acid or base. NaF is called a basic salt because it is formed from the neutralization of a base, in this case F-. An acidic salt is formed when a weak acid is neutralized by an anion such as Cl-. So let's take a weak base of ammonia. And occasionally in ammonia, a weak base will pull a proton away from a water molecule like this, and then it becomes the ammonium ion NH4+. That's a conjugate acid of ammonia. The water molecule becomes a hydroxide, and that's the definition of creating a base, as you create hydroxide ions in the solution. An acidic salt is formed when a weak acid is neutralized by an anion such as Cl-. The ammonium ion NH4+ has a 1+ charge. The halogen group, which is fluorine, chlorine, bromine, iodine, form 1- ion. So go and see your charge number by ion sheet if you want to confirm that. Chloride takes 1 electron to form a 1- ion. An acidic salt is formed when a weak acid is neutralized by an anion. The ammonium ion NH4+ has a 1+ charge. The NH4+ creates an ionic bond with the chloride ion to form ammonium chloride. This molecule is called ammonium chloride. It is a neutralized ammonium acid molecule. A neutralized acid molecule is called an acidic salt. So now you understand the concept of salts. You just take an acid or a base, a weak acid or base, and you attach a charge to them that makes them neutral, electrically neutral, and you no longer have an acid or a base. So let's review. Hydroxide OH- has such a strong pull on protons that it will cause 100% of weak acid molecules to dissociate. So this means that every strong or weak acid molecule that enters the water will give a proton to a hydroxide molecule. So there you see that. Remember, weak acids won't always give a proton to a water molecule, but they will always give a proton to a hydroxide ion, and that creates a water molecule. You see 4H2O over there on the right. This is important because every strong base molecule, OH-, that enters a solution can be neutralized by a weak acid so that the pH of the solution does not change. So you saw that with our soldiers example, the Invaders, Defenders example a few slides back. A strong acid, HCl, is placed in aqueous solution of a weak base, F-. The conjugate base of HF. Will the protons donate to the water molecule or to the F- ions? And where do those H+ protons attached to the 4 hydrochloric acids, where do they want to go first? Do they want to go to the weak base, which is fluoride, or do they want to go to the water molecules? Because we know a strong acid will donate a proton to a water molecule 100% of the time. But which would they rather go to first? The strong acid H+ protons will first dissociate to the weak base fluoride ions F-. Only after all of the fluoride F- ions have been consumed does the HCl dissociate to water to create hydronium ion. And that's what you saw in the second slide of the Invaders, Defenders. You had more Invaders than you had Defenders. In this case, the Defenders are the F-. So you ran out of those, so that last chloride, hydrochloric acid, donated its proton to a water molecule to create H3O+, and that's what you don't want to happen if you're trying to buffer your solution and keep the pH the same. So to create a buffer, we need the following. 1. To choose a pH you want to hold stable. Choose a conjugate weak acid-base pair with an acid pKa equal to the desired pH. Now, we haven't covered pKa yet. We will do that in a future lesson. But just remember at this point, you want the pKa to equal the pH. 3a, you use an equal number of moles of weak acid and its conjugate base salt, or you can create it in the other direction. Use an equal number of moles of a weak base and its conjugate acid salt. So those are the two ways you can create a buffer. 4, determine the number of moles based on the quantity of acid or base to be neutralized. Sometimes you have to guess at what that number is, but you want to have as much buffer as you need to prevent the strong acid or the strong base from taking over. So creating a buffer, so we will use the weak acid hydrofluoric acid and its conjugate base fluoride ion for this example. First, we need to produce an equal number of moles of both HF and F- so we can guard against equal numbers of strong acid and strong base molecules. So we will use simple numbers and say that 1 out of 5 hydrofluoric acid molecules will dissociate to produce a fluoride ion. This would represent the equilibrium concentration of HF and F- as 4 HF for every 1 F-. So what that means is the HF weak acid will guard against 4 molecules of Invader strong base. But over on the other side, the F- ion will guard against only 1 molecule of Invader strong acid. You'd like them to be equal. You'd like those numbers on each side to be equal. So the equilibrium concentrations of HF and F- will serve as a buffer. 4 times as many strong base molecules can be neutralized than strong acid. Now this is acceptable as a buffer. This would be a buffer, but it doesn't buffer equally in both directions, and that's what you want to have happen. So we would like these numbers to be equal. So the problem is if we add more HF, we will produce more F minus. However, the ratio of HF to F minus will continue to be 4HF to 1 F minus. So let's watch that happen. There it is, there's 4 to 1, and then you keep adding hydrofluoric acid, you get 4 to 1, 4 to 1, 4 to 1, because that's the equilibrium. We're just saying in this example, that's going to be the equilibrium here. So you never get the same number of F minus as HF. It just will never happen if you just keep adding HF. So how do we add F minus ions without adding more HF molecules? The answer is we use a conjugate base salt for HF, such as NaF. We will add 5 NaF base salt molecules to the solution. So there's 1, 2, and there's 5. So what's going to happen to those molecules the moment they hit the water? So what's going to happen is those sodiums, according to solubility rules, the Na plus ions completely dissociate from F minus ions. Now we can see that NaF and HF both produce a common ion. We talked about the common ion effect a few lessons back, and that's F minus. From our earlier common ion problems, and according to the Le Chatelier's principle, the concentration of F minus ions is greater than equilibrium. This will push the reaction back toward the reactant side and hydrofluoric acid. So the excess F minus ions above the normal equilibrium concentration will push the reaction back to the left to create more hydrofluoric acid molecules. So there goes one of the fluoride ions back. And from somewhere, from a water molecule, it's going to collect a proton and become a hydrofluoric acid molecule. So we've accomplished our goal. We have the same number of hydrofluoric acid to neutralize strong base invaders and fluoride ions to neutralize strong acid invaders. This is how to create a buffer starting with a weak acid. A buffer is created by using a weak acid and the salt of its conjugate base. The buffer can now guard against OH- and H+ invaders equally. A buffer from a weak base can also be created in the same fashion using a weak base and its conjugate acid salt. So memorize this concept. A buffer is created by using a weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. Okay, so that concludes our lesson on how a buffer works, and we're going to do some actual calculations to create buffers in a later lesson.